Welcome to the Calculus C section. In this section, we'll be discussing areas and arc length in polar coordinates. So we have now introduced our new function, r equals f of theta, to account for situations where y equals f of x and x equals h of y are not acceptable. In order to find the area using polar coordinates, we use the equation a equals the integral from beta to alpha half r squared d theta. Now, this looks very similar to looking at a triangle, and when we looked at our coordinate plane, we remember that our coordinate plane actually looks something along the lines of this, with this being r and this being theta, so that makes a lot of sense. Now we can find arc length in polar coordinates. We know that in prior L equals the integral of ds, and that is how we found arc length in Calculus 2. However, ds was equal to either 1 plus dy dx squared dx, or ds was equal to the square root of 1 plus dx dy squared dy. So we know that x is equal to r cosine theta, and we know that y is equal to r sine theta. So what we want to do is we want to find a way to substitute in arc length using these methods. So there is a large proof that is available on the website, but what it comes down to is ds is equal to the square root of r squared plus dr d theta squared d theta. Now this makes sense because when we want to account for a curve, we want to account for its radius, we want to account for the slope that it's approaching, and it is parallel to the equation of ds in Layton's terms of rectangular coordinates. So I hope that helps with understanding areas and arc length in polar coordinates, and there's a bunch of information on the website. Thank you.